Hi, my name is Aditeshwar Seth. I teach at IIT Delhi in the Computer Science department, and I also run a social enterprise called Gramvani. Over the last almost 2 years, we have been working with the Irada team at GIZ on use of data science and AI tools in NREGA specifically. I'm sorry I can't be there in person, but thanks a lot for this opportunity to share more about some of the work that we have done over this time. Sustainable rural development is not easy. Ecosystems are very complex with many relationships between resources like water, soil, forestry, biodiversity, and with climate change, all of these relationships are becoming complicated and hard to predict. There's increasing incidence of floods and droughts, and seasonal changes are also impacting how people manage their livelihood. Plus, there's also a growing disconnect between the common good and individual good with growing social pressures of moving forward in life. At the same time, there's also a disconnect between short-term and long-term sustainability in ecosystems. NREGA, the way we view it, is a beautiful, comprehensive framework to work within this complexity. It enables the collectivization in communities in terms of being completely demand-driven. A lot of the works are focused on sustainable ecological management. It is meant to improve the citizen-state interface as well, which is very important for democracy. And it also creates livelihood opportunities by finding out ways in which people can augment their incomes and improve market integration. I'm going to talk about a bunch of use cases in which this complex ecosystem can be managed in a better way through the use of data and AI tools. For example, one use case that we've been working on is to assess the impact of water conservation and rainwater harvesting works like farm ponds. What we do over here is that we sampled almost 500 farm ponds from the agroecological zone 13, and which is the upper Indo-Gangetic plain. And what we did is that from these farm ponds, we started observing that what are the changes in vegetation cover, and we measure this through satellite indexes such as NDVI, the normalized difference vegetation index, and we measure that in different zones of influence, right? 50 meters, 100 meters, 200 meters around these farm ponds, what has changed? And to understand the kind of change, we have to compare this farm pond location with locations without farm ponds. These are called counterfactuals or control points. So essentially what we do is we adopt a difference in difference approach of seeing how areas after the construction of a farm pond change in terms of their vegetation cover as compared to areas without farm ponds. And to do this difference in difference, we use methods like causal machine learning, and we found many interesting things. For example, we found that during non-drought years, which are years of normal rainfall, the vegetation cover in locations around the farm pond improved by almost 18% as compared to areas without farm ponds. Now, this increase in NDVI, the index that we use of 18%, roughly corresponds to almost a 40 to 50% improvement in yield. And this is, of course, going to be crop dependent. And this tallies with many experience reports that we've heard on the ground, where people who had these farm ponds constructed, they tell us, right, of how with the presence of a farm pond, it helped improve soil moisture, it helped them get over times when they needed some other kind of protective irrigation. Similarly, during drought years, which are more significant times when there is dryness or there are extended dry spells, farm ponds also help, but to a smaller extent of about 2% improvement in NDVI. So it's not completely, doesn't help farmers completely tide over drought years, but it's still helpful. So now what we're going to do going forward is we want to repeat this for other agro-eco zones, because farm ponds will have different effects in different zones, and this would also correspond to different purposes for which farmers use these farm ponds. Another important use case is for planning, where we are trying to assess the vulnerability of different areas to drought. And we are doing this at very small spatial scales, as small as a village or a micro watershed, right? 500 to 1,000 hectares. So the way we do it is that using machine learning, we have built a method to automatically find out whether an area is under single cropping, that is, they're able to grow only one crop in a year, or under double cropping, where they're growing two crops, or triple cropping. And what we can then do is that we can find out that during drought years, how cropping intensity in a particular landscape was impacted and compare it with non-drought years. So this gives us a measure of sensitivity of the area to droughts. In the same way, we are able to measure the sensitivity of water bodies, that during years of good rainfall or poor rainfall, how much of this water body had water that we were able to detect through satellite images. And we also do this over time, that what's the amount of water during the monsoon months, during immediate post-monsoon, which is roughly the Rabi season, and then during the summer months. So based on that, we create indexes to understand the drought sensitivity of areas, and which can be useful when it comes to deploying funds. And just to give you a quick sense of how this machine learning method works for intra-annual land use and land cover classification. Intra-annual meaning that we want to detect that within a year, how many crops were grown in that particular location. So what we do is, we, for each satellite pixel, which is about a 10 meter by 10 meter pixel, yeah, we take the entire time series. The satellites revisit areas every 5 to 6 days. So the system that we use is called Sentinel. And these satellites revisit areas they take a snapshot every 5 to 6 days. So we can therefore build a time series over an entire year of the spectral signatures that the satellites are observing. And based on this, we apply machine learning to see whether we can detect if there's, for example, one peak, it roughly corresponds to a single crop, or if there's 2 peaks or 3 peaks, right? We can detect that cropping intensity. Now, we also want to make sure that the classifiers that we build are robust and they can work in a diversity of settings. So for this reason, we sample points from across the country from different agroclimatic zones, so that a classifier has seen many, many diverse settings. So this is a product that we've released in the open source on the Google Earth engine. Anyone can run our scripts, and in less than 5 to 10 minutes, we can produce the land use land cover classification for any district for any given year. And we are also trying to extend this as far back as 2003, so that you can actually observe these changes over the last 2 decades. We are also trying to extend this to adaptive social protection in general. The way we are doing this is that for small spatial scales like villages or micro watersheds, we are first trying to classify them based on their terrain characteristics. That is this area a mostly plain area, or is it a mix of plain and slopey areas, and so on. Then based on the meteorological characteristics, that do they get high rainfall or are they in arid climates. Then based on land use, right, how much of the plain area is under single cropping or double cropping, and so on. And finally, on vulnerability and forecasted vulnerability, like extreme weather events being forecasted with the changing climate. So with this method, we will essentially have what we're calling a classification system at a very small granularity, spatial granularity, which we can take to experts who've been working on watershed development, on ecological restoration, and we can work with them to find out that what would be the best kind of action strategies for each of these different areas. This can guide very targeted, fine-grained planning. Yet another use case that we're working on is to find out whether NREGA funds are being deployed in a socially just and equitable manner. So here's how we do it. At a panchayat level, we have data on the amount of NREGA expenditure that's been happening over the years. So one way to think about it is to compute basically what is called the per capita NREGA expenditure, right? NREGA expenditure divided by the population of that panchayat. This, in the extreme left figure, you can see shows that there's a wide variation. Some panchayats are getting a lot of NREGA funds, some are getting very less. But on the other hand, this could just be because the panchayats getting less actually don't need NREGA. Yeah, they are probably closer to urban areas with less agriculture and so on. NREGA is of course a demand-driven scheme, as we all know, and therefore one way to correct for this possible bias is to just look at expenditure based on demand, right? Based on how many demands were registered. This, as you can see, gives a more equitable picture. Yeah, but we do know, based on our own field experience and so many experience reports, that demand registration has biases of its own. There are awareness gaps, not everyone knows how to demand work, and it also depends a lot on the management and the rigor with which NREGA is implemented in an area. We therefore use machine learning again to build a demand prediction model. Yeah, that if everyone were potentially aware of NREGA and its benefits, how much demand would actually come in? And if we normalize the expenditure based on this, this is where we see a true variation. And what we're trying to do now is to build a dashboard that we can present to administrators, using which they can actually target areas where greater mobilization might be needed. Because our hypothesis tests and everything indicate that a big reason behind this bias is actually gaps in the awareness of people about what NREGA can be used for. Finally, I want to talk about one of the latest breakthroughs in the field of AI and machine learning of what are called large language models like ChatGPT. Over here, we can use some of these latest developments to improve the citizen and government connect. Systems that we have built, over here users can call, right, using phones, or we can also make this accessible over WhatsApp or over an Android app, and they can just speak in their regional local language. And through this, they can record feedback about problems they're facing, or they can register grievances or register demands. We use speech recognition to convert this speech into text, and then we use some of these large language models to uncover insights and nuggets from this information, like what is the specific location, what are the problem details, what is the type of NREGA scheme, for example, that people want to demand. And these can then be delegated to field cadre or to, let's say, CSOs or social welfare organizations working in the area. So in this way, you can actually have a seamless pipeline from having users put in their demands, and the field cadre can then enter them into forms of this sort, where they can help people register demands for different kinds of natural resource management structures, and potentially with the click of a button, they can register, they can create an entire DPR, a detailed project report, which can be put up in the Gram Sabha and thereon taken through the approval process and allocation process. At the same time, we should also be cognizant that people will not be able to use such systems unless they're made aware about their existence, and in general aware about different kind of opportunities that they can avail under NREGA. For this, a simple innovation that we're doing in the Irada project is to send voice-based advisories to farmers. Specifically, farmers who've taken up mango plantations are sent advisories on how to maintain these plantations, how to watch for infestations, when to trim the canopy, and so on. In the same way, we are sending information on goatery, on mushroom farming, and several other topics. There are many more opportunities. We're also working on automated water budgeting, where we're using climate data about rainfall that happens in a particular area. We compute the runoff based on the slope and other hydrological properties like the soil group at that point. We use evapotranspiration data products, and we are then able to compute whether a particular area is in water surplus or water deficit. This can again be used to build targeted planning for more efficient groundwater usage. Another area that is exciting is on downscaling some of these outputs, where, for example, we take evapotranspiration and we're using machine learning to downscale it so that we can actually detect that from individual farm fields how much evapotranspiration is happening. And that can potentially, we have yet to make progress on this, but that can potentially be used to detect areas where over-irrigation is happening, and potentially plan on how greater awareness campaigns can be launched in these areas for more efficient irrigation use. Similarly, tree plantations like mango plantations, which have shown to be very, very effective in improving livelihood. We can build ways using satellite data to monitor some of these plantations and their health, and potentially also provide advisories to people. I'll also just add that a broader tech stack that we're building around climate change adaptation called the core stack in collaboration with a large number of collaborators. So we're trying to make all of these innovations that I spoke about and many more available in open source through open data in a manner that can be accessed by anyone, any organization. And yeah, so please do write to us. I've given these emails, and look forward to working together and taking some of these innovations to scale.